All right, so let's talk about changes of state of matter. So we're going to describe the changes of state between solid liquids and gases, and then also calculate the energy involved. I know we're excited about this. So matter undergoes a change of state when it's converted from one state to another. At a constant temperature. Okay, so changes of state include melting and freezing, boiling and condensation, and then what we have is sublimation and deposition. Okay, sublimation and deposition are a little bit different than what you're accustomed to. Sublimation is like CO2 when it goes from a solid directly to a gas, and then deposition is the exact opposite, going straight from a gas to a solid state. All right. So a substance can change from a solid to a liquid at its melting point, and then change from a liquid to a solid at its freezing point. In the case of water and other materials, in the case of water, it's zero. Okay, that is both its melting point if we're putting more heat into it, and its freezing point is if we are taking heat out of it. So that would be, melting point, freezing point is perspective. So, water has 334 joules of heat is needed to melt 1 gram of ice at its melting point, 0. So if we look at this, we go from a solid to a liquid by introducing 334 joules per gram of heat, and that is an endothermic reaction. All right. Now, the reverse of that is freezing. H2O to go from a liquid to a solid, 334 joules of heat must be removed to freeze 1 gram at its melting point. That is exothermic. So we got endothermic and we got exothermic, all right? Cool. So let's say, we've got our constant, this 334, all right here. And we know, let's say we wanted to figure out how many grams or how much heat is needed to melt this 15 grams of ice. All right. So we know we have 15 grams of ice. We know that the heat fusion joules is 334. So simply stated, we can just go 15 times 334 is going to leave us with 5,010 joules. That is how much energy, heat is needed to melt 15 grams of ice. If it was 30 grams of ice, we'd multiply 30 by 334, end up with 10,020 joules of heat needed to melt that ice. Pretty straightforward. So evaporation, that occurs when water molecules gain sufficient energy to escape the liquid surface and enter the gas phase. So here we can see the thermometer's at 50 degrees. Well, we know water doesn't boil until 100 degrees. We got some bubbling and some activity going on because the molecules are starting to rock and roll, but there's not enough to actually escape the liquid form. So at the boiling point, the molecules have enough energy to overcome their attractive forces and become a gas, okay? So once we hit 100 degrees, boom, they're excited and they just get out of there. And you can feel that in boiling. When you put your hand over it, you can feel the steam or the gas and water molecules colliding with your hand. Then condensation. So if we do it at 100 degrees, if we capture that water vapor, that gaseous water at 100 degrees and drop that temperature, what's going to happen? It's going to condense and then turn back into a liquid. Think of a clear lid on a boiling pan. Well, what do you always have on the surface of that clear lid? Well, water, liquid water. Well, why? Because that clear lid is reducing the temperature of those water molecules to less than 100 degrees Celsius, causing it to liquefy once again. So we go from vaporization and then back through condensation. All right. So here are some heat fusion for some and heat evaporization for some common substances. Water 334, ethanol 109, acetone 99.3. Boiling point of water is 100, ethanol 78. And, I always like to say, like, hey, Colin, your liquor glass is getting light. And I'm like, well, that's because the energy to cause it to vaporize is much less than what it would be if it was a glass of water. Now, obviously, that's a lie. I'm drinking it, but it makes me feel better about myself. All right, so when you see the type of bonds, okay, and the joules needed based on bonds, okay? So if it's a polar covalent bond, non-polar covalent, very little energy is needed, or joules per gram is needed, and versus polar covalent. And then remember, we said ionic bonds have the strongest bonds, so much more energy is needed for, much more heat is needed to get those to melt and boil, okay? So heat of vaporization for water can be used as a conversion factor, okay? It's a constant. So heat equals mass times the heat vaporization, so it's 2260 joules per 1 gram of water. So if we had 10 grams, well, that would be how many? 22,600 joules of heat, okay? So 50 grams of steam, 100 degrees Celsius. We got 50 grams, okay? We need to know our constant, 2260 for water, and then we want to know kilojoules, so we need our conversion factor of 1,000 joules are in 1 kilojoule. So we set it up. 50 times 2260 divided by 10 gives us, or divided by 1,000 gives us 113 kilojoules, all right? It's pretty straightforward as long as you set up the equation appropriately. All the changes, say, during the heating of a solid can be illustrated by a heating curve. Heating curves are a graph with the temperature on the temperature, the vertical axis, and addition of heat on the horizontal axis. Heating curves illustrate the change of state. So if we look at this, we've got these plateaus here, boom. All right, that's a change in state of matter. Then temperatures increasing, so the energy in the molecules are bouncing more and more and more. Then we hit 100 degrees. We go into the gaseous state and then above gas, okay? So these are all rises, and the plateaus are changes of state, okay? The reverse would be the same. As we cool it down, it condenses, cool it down, it freezes. Plateaus are states of matter change, okay? And then we call it freezing, but if we reverse this graph, then it is boiling, or melting, okay? We call it condensation. But if we reverse it, it is boiling. So, yeah. These are combined energy calculations, just depending on what you look for. Biggest thing is to know what you're starting with and what you need to end with. Okay? Joules per gram Celsius. Joules per gram for liquid. So these are states of matter. Okay? And these are changes in the matter, so melting and vaporization, all right? So the plateau on a horizontal line on a heating curve represents what? A change of state. Slope line, a change in temperature. Very good, all right. So using the cooling curve for H2O, let's answer each. Water condenses at the temperature of, well, we know it boils at 100, so it will condense at 100. At a temperature of 0, liquid water will, well, it's a liquid, so we go to a solid. If it was a solid, it would, what happened? If it's solid, it would melt, okay? When water freezes, heat is added or removed. Well, let's see, if something is freezing and it's getting colder, so let's say removed. And there we are, 100 freezes and removed. Produce a fever. Okay, so let's calculate some energy. We're going to use a pack that's 250 grams of ice, solid. If the ice is at 0 degrees Celsius, it melts warm body temperature 37 degrees Celsius. How many joules are removed? Well, first we got to deal with 250 grams from a solid to a liquid. All right, so let's start there. We had mass times the heat fusion. So in the case of water, it's 334 joules. Okay. And then we're given the SH water at 4.184 joules. Okay, that's how much it will, joules energy per degree it will change. Okay, so let's start with the energy needed to change it. 250 times 334 gives us 83,500 joules. Now, for every degree up, okay, we're going to go 37 degrees, and we have 250 grams times 37 degrees, because going from 0 to 37, times 4.184, 38,700. We then add those together for a combined total of 122,200 joules. That's how much it's going to take to get that water, how much heat it's going to take to get that 250 grams of water to 37 degrees C from 0 degrees C. All right, so I hope this kind of wraps up the chapter. I hope you understand it all right, and have a good one, guys. See you tomorrow.